The session is called here New Added Value Through Key Components. One of these key components on the way to electric mobility, of course, is the electric motor. We already heard from Professor Fleischer that it's very important to produce them agile, and one of the actors really producing electric motors in Baden-Württemberg is the company Schaeffler Automotive in Buehl, and the presentation, he's not here in person, he comes to us in the digital space. Thomas Pfund, he is president of the e-motors and PEU business unit at Schaeffler Automotive in Buehl near Karlsruhe. And the title of his presentation is Motors for Future Powertrains, Key Component or Commodity.
Welcome to my presentation. Today I want to discuss the question if e-motors for future powertrains are key components or rather commodity products. If we discuss mobility today, it always starts with the environmental impact. So climate change is the most relevant technology driver. And for CO2, legislation is already in place. We are discussing Euro 7 for emission regulations. What is not that much in the open discussion yet is the CO2 neutral production. That's why Schaeffler did a self-commitment to achieve CO2 neutral production by 2030. Looking a little bit deeper into these CO2 targets, we see that targets are in place around the globe, which is good news. The most challenging targets are in Europe because we are considering in Europe all greenhouse gases, not only CO2. And look on the lower left side of this chart, we see the fleet target value for 2021 with 114 gram per kilometer. So this is the CO2 legislation. You might ask, why not 95? Because 95 is the value belonging to the NETC cycle. We have changed this one to WLTC. And we transferred this value for this chart here with a factor of 1.2 to this 114 grams. So, but it is exactly the European legislation. So this one will change. In the discussion is the amount of change. We think that the value will be reduced by 50%. That's why we come to this 57 gram per kilometer in 2030. So this all is considering the so-called tank-to-wheel model. So only fuel out of the tank to the wheels or energy out of the battery to the wheels. So in my opinion, this is not right because also in production of fuels, production of energy, and production of the cars, recycling and so on, we emit CO2. So that's why we should take this into account if we want to discuss zero CO2 really at 2050. So we think that around 2030 also this model will be changed in connection with the new target values, and maybe on the way to 2040 we should change to this LCA, so life cycle assessment approach or cradle to grave approach. So coming from this target, we investigated what would this mean for the technologies. So, and we think that we will see a technology mix in 2030 of almost 30-40-30 scenario, 30% pure combustion engines, still 40% hybrids, and 30% pure electric with strong growing share of the pure electrics toward 2035. So this is the view for the world market. If we look into Europe and take this minus 50% into account, then we think that we would need in 2030 a share of 61% of pure electric plus plug-in hybrids. Where does this come from? I want to show this in this scale model here. We see these different colored bars. These bars are showing the technology, so starting with the pure combustion engine technology in the gray bar, and then the different steps of electrification with the impact on the consumption up to 100% with xEVs. The supporting point of this scale is exactly the target value of 114 gram, and the position of these bars is the CO2 value of this technology. So, the height of this bar simply shows the volume, so the number of the cars in this technology, and the car manufacturer now has the target to balance this scale. So, because if it would turn left, this would be bad because the car manufacturer would have to pay penalties. If it turns right, would be good. He could trade with the CO2 certificates. So this changes towards 2030, and we see that with this change, we need an increasing share of plug-in hybrids and xEVs to keep this scale in balance. So you might ask, why not xEV only and no plug-in hybrids? So this is because there are some boundary conditions, and boundary conditions are availability of renewable energy. It is also the grid to distribute this energy, and it is a question of energy storage to leverage this. So, and this can be seen in this chart here. This chart shows the renewable energy share in Germany in 2020. And we can see that it is a significant share already, which is good news. But we also can see that this energy supply is very volatile, so it depends on the weather, and that's why we would need storage technology and capacity to leverage this. The EIA did a study on this, and they found out that if we want to leverage this in a world view, that we would need at least 10,000 gigawatt hours of storage capacity. And this equals 50 times bigger size of the current market. So a huge challenge, and this cannot be done with additional stationary batteries only. We will need additional and parallel energy bases. So if we imagine we have this renewable energy on the left-hand side, then we could take this energy and put it directly in the battery of a car and drive with this. This is the shortest pace, the best one in efficiency too. So what we talked about storage, if we have to store, we could do this in stationary batteries, redox flow, whatever technology. And then we could take the energy out of this storage device and put this into the car. This reduces the overall efficiency, of course, and we have to consider that not all storage can be done by additional batteries. So we need other technologies. And next technology could be the hydrogen. So we use the renewables to produce hydrogen. Fill this into a fuel cell and drive with this. Or we could use this hydrogen, taking also CO2 and produce synfuels. Synfuels could be gas, could be liquid. And the good one on this solution is that we could use the available infrastructure. So all the gas stations which are out there available could be used. And if we then use this PF technology as well, we could even have a okay efficiency. So this energy paces and different technology we will need in the future. So looking into technology to influenced by this different pace. So we will see hybrid powertrains and EV powertrains in parallel. In the hybrid portion, main technologies are hybrid modules and DHTs. Hybrid module I will explain in the next slide. This DHTs means dedicated hybrid transmission. These are transmissions designed, dedicated for this hybrid usage with two energy sources or power sources, the combustion engine and the electric motor. So, and in the portion of the EVs, the dominating technology will be e-axles. But there we will also see different power demands, different car sizes. So we think we will have powers between 50 and 500 kilowatt or even more if it comes to heavy-duty trucks. And we have different use cases, the main drive or all-wheel drive. So this e-axle technology also has to be adapted to the application at the end. So taking out these three main technologies, hybrid module is a system which sits in between the combustion engine and the transmission. So the e-motor is connected to the crankshaft of the combustion engine. That means speed range is the same. And the e-motor can drive through the transmission. So the e-motor load points are supported by the transmission for recuperation and electric driving, which is on one hand side a good news because we can adapt the load point of the e-motor, choosing the best one. On the other side, on the downside, we always have to deal with the efficiency of the transmission. So DHTs, multimode is the answer of Schaeffler to this technology. There are different solutions out there with one electric motor, with two electric motors. We have chosen a system with two electric motors, which is shortly explained. So the motor one is directly connected to the crankshaft, and the motor two is connected to the differential gear, so to the wheels. If we switch off the combustion engine, then we can run the vehicle completely electrically with the e-motor 2, so this feels like an electric car. If battery runs low, then you can start the combustion engine and run the e-motor 1 as a generator. This is the second mode, so this is like a range extender or a serial hybrid mode. And the third mode is closing the clutch between these two electric motors, and then the combustion engine is coupled directly through to the wheels, and we can drive at high speeds on the motorway or autobahn with best efficiency. And the combination of these three modes gives us a very good overall cycle efficiency. So last but not least, in this row, the e-axles for hybridization, also possible, but also the main drive for pure electric vehicles. We have today integrated systems. We call it 3-in-1, motor, transmission, and power electronics in one package. And the motor is connected to the wheels via a 1-gear or 2-gear transmission, depending on the application. So, and what I did is, in the next slide, showing the power demands, the torque and speed demands, and the area of best efficiency. What you can see in this chart here is the load points, which are driven in the different driving cycles. And the yellow and red color shows the highest shares of these load points. So, and you can see that this is completely different depending on the application. In case of the P2 hybrid, the most driven load points are at lower speeds, are also at lower torques, because the transmission helps. And we have a yellow area there in the minus torque range. This is the recuperation and generator mode. In the middle of this chart here, the multi-mode DHT, we see e-motor 1. I explained this already, that this motor is running as a generator. You can see this red area there. This is exactly the generator mode. And the e-motor 2 is running as the drive motor, so the load points are completely different. And that's why we also have to adjust and design the motors different to put the area of best efficiency to other load points. And e-axle is also a drive motor. You can see this is similar to this e-motor 2 of the DHT. So this is power requirements and the area of best efficiency. There are also in parallel constraints coming from the package, from the design space. So if you look at a hybrid module, you can see this is sitting between combustion engine and transmission. There's not much axial space. That's why it has to be short. And we want to integrate into the rotor of this motor additional port like clutches. That's why the motors are bigger diameter and very short axial lengths. And if we compare this with a motor for e-axle, you can easily see that this looks completely different. And this has already influenced then on the production technology we want to use. So for these very short motors, we are still using so-called concentrated windings due to the small winding heads we get. And for the other solutions, we are using distributed winding with a special technology we are developing in Schaeffler as well. So, and this is also very important fact that you influence the behavior of the motor directly by the production technologies. So winding technology influences the copper fill factor, for instance, and therefore the efficiency. The stamping influences with the punching edges the behavior of the steel. So also the loss behavior is also efficiency. So we really have to develop not only the product, the motor, but also the production technologies we use. So how can we cope with these different requirements in the development view? Developing a new motor is always a balancing task of competing goals. So we have to be good in meeting performance targets, in meeting efficiency targets. We also have to consider the excitation the motor brings. That means this is the acoustic behavior. Material costs is important, and so on. So, and the problem is that these targets are really competing. So if I improve the acoustic behavior, it usually have a negative impact on efficiency and peak performance. So that's why we always have to take into account what is the installation, what is the application, what is the target of this system. So we need system knowledge to do a good optimization of the motor properties. The other one is to use the methods. So there are a lot of design parameters we can change, and this gives us a huge number of combinations. It's millions. And this is what we do then. We have optimizers running, calculating all these different combinations and find out at the end what the best fit is to the requirement set. And this is based on tools for single task, like the FEA analysis for the magnetics, for the mechanics, for the thermal behavior, then the dynamic behavior, eigenform analysis, multi-body simulation, down to simulation of our production technologies and factory simulation. So we try to virtualize this, or we already have virtualized this whole tool chain And with these tools and tool chains, we have excellent specialists to use it and to find the optimal solution for the application. And this has to be done for every single application. So I cannot take one motor out of one application and put it in the other. I can do this, but the result will not be the best. So for production, this means that we have to have a deep vertical integration. I already explained the influence of the technologies to the properties of the product. That's why we are developing in parallel the production technologies in parallel to the product. And we also have to cope with the fact that the investments are high, that we have to have a very high utilization to achieve good production cost. And this is why we install this all inside our plants to have this in our hands. Second one is how we combine the technologies, so the process flow. For high volume production, it's well known to use these high volume transfer lines where the product is running from station to station. This is good for low cycle times, but it is not very good if it comes to sudden changes from one product to the other. And since we see, due to these different technologies for hybrids and pure electrics, and the fact that the single project is also volatile in terms of volumes, we think we have to be very flexible in the future. And that's why we need, at least in parallel, new approaches for production concepts to not directly link the machines to each other, to be flexible in terms of technology of the product and also in volume. To achieve this, it's also well known that the requirements to logistics, how the parts flow, is very high. That's why we really need new technologies. We need approaches like digital twins, Industry 4.0. This is necessary to introduce such kind of line concepts. And last but not least, we have to cope with the challenges coming out of the environmental impact. I mentioned this already, so all new plants we build or refurniture old plants for these new tasks, we have in mind to make these plants CO2 neutral. So in coming from this approach is using these newest technologies and developing this, we are able to produce these motors in first step, of course, around the globe, exactly there where our customer sits. But we also are able to produce motors and develop all these processes in Europe, in Germany. And this was our decision from last year, that we have the headquarter for e-motors in Germany, that we also have the leading production segment in Germany and the process development center. And to achieve this also to achieve the necessary costs, we have to combine this with ultra-efficient production approaches, with very good local supply networks, and so on. But using this, it becomes possible. Key component or commodity? Yeah, this was the initial question. I want to do a short summary. CO2 legislation has a big impact, and this leads to technologies we will see in parallel, so plug-ins and pure electric powertrains. We will see different energy pace, coping with the renewable energies, which are very necessary. And the storage of this energy will be a challenge. We will see the hybrids beside the pure electric powertrains. If it comes to the e-motor, then we have to have different e-motor solutions for these different powertrain technologies. And we have to connect this to the production technology because the e-motor performance is directly influenced by the quality of production technology. And at the very end, last but not least, e-motor influences directly customer relevant properties. So with this efficiency, its influence on the driving range, its influence on package performance, on weight, on cost. And a system is at the end as good as its components. So I think that there is a good chance also for the e-motor and a big necessity to be developed further according or in connection with the production and the production technologies. So I think yes, we will see high volume production. This might count for this commodity, but there will also be a lot of additional development we will see, and this is then rather the side of the key component. So this is the end of my presentation for today. Thank you very much for your attention.
So, thank you very much to Thomas Pfund, President of the e-motors and PEU business unit at Schaeffler Automotive in Buehl near Karlsruhe. Thomas Pfund could not be here with us today, so as you saw in the background of his presentation, we visited him in his office and recorded his presentation in advance.